All right, so this is going to be the first video in our new unit on chemical reactions, and it's going to focus on electrolytes. So when you have an ionic solid and it is being dissolved, the ions that are present in that ionic solid that are oppositely charged have to be separated. Water is able to do this because it has a partial negative end with the oxygen and it has partial positive ends with the hydrogen atoms. And so when water molecules surround those cations and anions, the positive cations are drawn towards the negative electrode and the negative anions are moving towards the positive electrode. With that happening, the ions are then able to conduct charge. So here's more of a molecular level of what's happening with the solid, the positive and negative ions, the cations and anions, and how they are being surrounded in the case of the negative anions by the positive hydrogen atoms present in water, and in the case of the positive cations by the negative oxygen atom that's partially negative charged present in water. When you are a strong electrolyte, all your ions are able to do are to dissociate. They separate into, the compounds separate into their two ions, and they allow the current to flow extensively. When you are a non-electrolyte, none of the molecules are able to be ionized. You don't have an ionic compound in water, and so you see no current flowing. But if you're a weak electrolyte, you have the ability to separate into your ions to dissociate some of the time, but not always. And the amount you are able to dissociate is going to be indicative of how much light will be generated, how much current is flowing through those electrodes. In the case of strong electrolytes, they are going to completely ionize in the presence of water. I used an ionic solid as an example. If they are soluble in the presence of water, they are going to be excellent strong electrolytes. Metals that are in liquid form that are molten would also work as awesome strong electrolytes. And there are 6 acids that are able to completely dissociate in the presence of water: HCl, HBr, HI, H2SO4, HClO4, and HNO3. All of those are your strong electrolytes, and the equation that's shown there is depicting what would happen if you had a strong electrolyte placed in water. It would completely separate into its cations and anions. You also have a picture of sodium and chlorine ions in the blue box, showing you what would happen on a molecular level if you had dropped 4 molecules of sodium chloride into water. When you have a weak electrolyte present, sometimes ions will form, but oftentimes the compound will not break apart, it will not dissociate. Examples of weak electrolytes are going to be any other acid than the 6 we just talked about previously, any sort of weak base. The most common weak base is ammonia, but sometimes you can have one of the hydrogens or more than one of the hydrogens replaced with a carbon-containing group, and that would make it be an organic base. And you could also include tap water, since it contains trace metals that would be able to partially conduct that electricity. An example of a weak electrolyte equation is shown there. I want you to notice in the case of ammonia, because ammonia is a base, it accepts a proton from water when it is capable of dissociating, producing the ammonium ion as well as hydroxide. I also want you to notice that there is a double arrow because that reaction can move in both directions. And in the case of ammonia, it stays primarily as ammonia, which is why if you look at the pictures in the blue box, you will see 3 of the 4 ammonia molecules are still intact. Only one of the ammonia molecules actually went through dissociation to produce the ammonium ion as well as the hydroxide ion. So those 2 ions are the only part of that particular mixture that we're looking at that would be capable of completing the circuit. When you have a non-electrolyte, you have substances that are incapable of producing ions when placed in water. Your solids, your gases, any other molecular substance would fall into this category. If you have something like this that's acting as a non-electrolyte, it's going to stay in the same chemical composition on both sides of the equation. The only difference will be the form in which that substance is being represented. So here I've given you 3 compounds that are acting as strong electrolytes. These are all ionic compounds. They all start with metals. And I want you to write equations to show the ions that are made when each of these is added to water and the relative number of ions that are generated. So in Ki, potassium iodide, we would have a cation and an anion. The cation would be potassium, the anion would be iodine. If we go to our periodic table, because potassium is in group 1, it has a +1 charge. Iodide is in group 17, it has a -1 charge. We only had one of each, so that is a balanced equation. In our second example, AlBr3, we would have 2 ions again, aluminum acting as our cation and bromine acting as our anion. Aluminum is in group 13, so it would have a +3 charge. Bromines with iodine, it would have a -1 charge. But because there are 3 bromines that were present in that molecule of AlBr3, when I write the chemical equation, I would want to show that because 3 -1s would balance out with the +3 of aluminum. And so the total charge on both sides of the equations should be equal. And that was what would make the aluminum bromide that was initially at a charge of 0, that was neutral. Its ions, when they separate, would also still leave you with a neutral charge. In our final example with barium hydroxide, we would be splitting this compound into barium ions and hydroxide ions. Hydroxide has a -1 charge. Barium is in group 2. It has a +2 charge. There are 2 hydroxide ions present in this compound, so that's why you see the coefficient of 2 in front of OH. Then this is just reviewing very quickly what is classified as a strong, weak, or non-electrolyte. In our first example, we do not have an ionic compound, nothing starting with a metal or ammonium. We do not have an acid. We don't have anything starting with H. We don't have NHs in this compound, so it's not a base. But it is made of just nonmetals, so that would make it a molecular substance, and that alone would make it a non-electrolyte. The fact that it is in its solid state absolutely would make it a non-electrolyte. So that it is molecular and that it is solid are both reasons why this is classified as not conducting current. It would not produce any ions in water. HBr in its aqueous form is one of your 6 strong acids, so that would be a strong electrolyte, and so it would completely dissociate. And then our final example, we don't have an ionic compound. CH3 is not a metal or ammonium. We don't have an acid. It doesn't start with H, but we do have a base. Remember I said any compound that contains that nitrogen could also act as a base. Now, if it's part of a polyatomic like nitrate, that's a different story. It's got to have some sort of carbon-containing group and something that appears like ammonia. So this is methylamine, and because it is only capable of partially dissociating, it would be classified as a weak base. And then our final example with electrolytes, show this in the boxes below what you would expect to see on a molecular level when you have 3 molecules of each of the following, and these are all in aqueous solution. So we just need to determine whether they are strong, weak, or non. We don't have to worry about states this time. What would happen when they're added to water? So our first example, calcium nitrate, well, calcium is a metal, so that's an ionic compound, and because we know that's aqueous, we know it's going to completely produce ions. It's a strong electrolyte. So 1 molecule of calcium nitrate would produce 1 calcium ion and 2 nitrate ions, because there's 1 Ca and 2 NO3s present. A second molecule would do the same, as would a third. All we are producing are ions when we have a strong electrolyte. With CO2, it's not an ionic compound. It doesn't start with a metal or ammonium. It's not an acid. It doesn't start with H. It doesn't have any NHs in it. So this would be classified as a non-electrolyte. So 1 molecule of CO2 would just give us 1 molecule of CO2. And the same would happen with a second and a third. In our final example, this time we do have an acid. It's starting with hydrogen, but it's not one of our 6 strong acids. So this would be classified as a weak electrolyte. So you have to have at least one of the 3 molecules intact to distinguish between strong and weak. I ended up having 2 of them intact. There's my first molecule, H3PO4. And my second molecule, again, as a weak acid, it's only going to pull off one of those hydrogens at a time, which would leave you with H2PO4-. And then the third molecule would be intact.